Probability and Statistics seminar. I moved to Caltech last year and actually still haven't had a chance to visit USC, so I was really looking forward to being able to come in person to meet many of you, but it's still wonderful to be able to tell you what my group has been up to virtually, and then hopefully I'll be able to meet some of you in person soon at USC or Caltech. Anyway, so many things that we want to take pictures of, we can actually see with our own eyes. And using a standard camera, we can produce a picture of an image that looks like the scene we want to capture. So it might be slightly noisier or blurrier version of that input that that image that we want, but it's still roughly the targeted scene. But in many cases, what we want to image is actually invisible to us. So for instance, we can't take a picture of our brain using a standard camera. And so in these cases, it's impossible to directly image the thing we want to see. And so people have developed alternative ways to take indirect measurements, for instance, using an MRI scanner. And in these cases, the measurements don't look anything like the image we're trying to capture. And so to deal with this, we develop algorithms that work with the sensing system in order to recover this desired picture. And so this class of problems is called computational imaging. And in my work, I've worked on applying this methodology of designing sensing systems simultaneously with algorithms in a number of different kinds of domains. But today I'm going to focus mostly on telling you a little bit about how we've been able to use this methodology to reveal what I think of as the ultimate invisible, black holes. So black holes are one of the most mysterious objects in the universe, and scientists have been studying them ever since they were first predicted by Einstein's theory of general relativity just over 100 years ago. And in particular, for decades, scientists have been studying the giant elliptical galaxy at the head of the Virgo constellation. So this galaxy, called M87, is 55 million light years away from us, and it's very special because over 100 years ago, someone discovered a streak of light on the sky, which ended up being this galactic scale jet of plasma that was shooting out of the center of the galaxy and marking the spot of a supermassive black hole. And so over decades, scientists have tried to develop better and better instruments in order to study this supermassive black hole predicted to be at the center and the jet that's coming out of it. And in April 2017, we hooked up this Earth-sized telescope and collected the data necessary to make the first picture of a black hole 2 years later. So this black hole image was the result of a group of hundreds of scientists from all around the globe that were working together to build this computational Earth-sized telescope in order that we needed to take this picture. So today I'm going to tell you a very, very abridged story of how we were able to capture a picture of a black hole. There are kind of many different angles to the story, so I'm going to give you a glimpse into kind of the primary contribution that I worked on for this, and that was how the imaging was done and validated. And then in the second half of the talk, I'm going to talk a bit about techniques currently being developed in my group at Caltech to push the Event Horizon Telescope past its current limits. And in particular, I'm going to talk about new methods that we're developing now on doing uncertainty quantification of images with the Event Horizon Telescope kind of data, and as well as how we were developing machine learning methods to optimize the placement of the next telescopes we build into this Earth-sized telescope array. But before I get started on explaining how we do imaging, I want to try to answer the first question that many people have, and that's how do we even, are we even able to take a picture of a black hole that by definition doesn't let light escape? It's by definition unseeable. Well, light propagating near a black hole doesn't actually follow straight lines. It's curved because the black hole is curving space-time. And so photons can even go in complete circles around the black hole. And so the space around a black hole is actually lit up by this hot gas that's spinning around. It's heated to hundreds of billions of degrees. And so you have these photons flying around everywhere. And some of these photons fall into the black hole, but other ones just graze the boundary and are bent by the black hole's gravitational pull, such that the net effect is that the black hole casts a shadow on bright surrounding emission that's almost perfectly circular. And if Einstein was right about general relativity, I don't know why it's, oops. I don't know why it's doing that, but okay. And if Einstein was right about general relativity, then this light would be bent into a ring whose size and shape are telling us about the mass and the spin of the black hole. And so this ring is referred to as the black hole shadow. And before I was showing you this perfect ring, but in reality, this is what a more realistic simulation would look like if could see, you know, with something very, very high resolution and at about a 1 millimeter wavelength. And so it turns out at first glance, taking a picture of this ring actually seems almost nearly impossible. And that's because this ring is incredibly small. It's about 40 microarcseconds in size, which is about the same size as a grain of sand. But when that grain of sand is in New York and we're viewing it from Los Angeles. So taking a picture of something that small is really, really difficult. And it all comes down to basically the limits of diffraction. And so what diffraction says is that if we plug the wavelength of light and the required angular resolution we need to see that black hole shadow into the diffraction limited equation, we can calculate that in order to see the black hole ring, we would need to build a telescope that's 13 million meters across, or essentially the size of the Earth. And if we could build this Earth-sized telescope, we could just start to make out the distinctive ring of light that's indicative of the black hole's event horizon. And so although building a single dish telescope the size of the Earth isn't possible, by joining telescopes around the world, I've been working as part of an international collaboration called the Event Horizon Telescope that has built a computational telescope the size of the Earth, capable of resolving structure on the scale of a black hole's event horizon for the first time. And so how does this computational telescope work? Well, the EHT is composed of telescopes from around the world that were actually originally built for other purposes. And by installing specialized equipment at each site and linking the signals through the precise timing of atomic clocks at each one of the sites, we've been able to make these originally disjoint telescopes work together. And so we have teams of researchers that we send out to each of the sites, and we collect the data by essentially freezing the light on petabytes of hard drives. And then our computers, we bring all the data together, and our computers process the data and act like the lens to make the final picture. And so my primary role in the project is working on constructing an image from the data taken from these disjoint telescopes. And so how do we do that? Well, unlike with a camera in the Event Horizon Telescope, we don't capture the picture in pixel space, but we instead capture it in its spatial frequency space. So we essentially take measurements of the black hole image's Fourier transform. And if we put telescopes all across the globe, we would sample all these spatial frequency measurements. But since we only have telescopes at a very few locations, that means we only get a sparse number of measurements. And so it turns out that for every 2 telescopes in the array, we obtain a single complex measurement of the underlying image's 2D spatial frequency that's related to the projected baseline between the telescopes. And so each of these measurements is complex. So every 2 telescopes gives us 1 measurement. Each of these measurements is complex. So it's described by 2 numbers, its amplitude and its phase, which is going to become important later. But still, in 2017, we had 8 different telescopes. They were, but only actually 5 of those telescopes could see the black hole in M87 and were at distinct locations. So that means with the EHT's 5 telescopes, that would have been 5 choose 2, only 10 points that we'd have to try to make an image from, which is an incredibly small number of measurements. But we get lucky because as the Earth is rotating, we actually obtain other new measurements. So since the projected baselines between the telescopes change as the Earth rotates, this amounts to carving out these different elliptical paths in the spatial frequency plane, where telescopes that are close together tell us about the broad structure in the image, and to get the fine detail to see the ring, we have to put our telescopes really far apart. So we get these measurements by recording hundreds of terabytes of data at every telescope. So here you see my friend Lindy Blackburn posing with about a half a petabyte of data that we collected just at the LMT telescope. And so in 2017, we collected about 5 petabytes of data, and we record so much data that we can't send it over the internet, and it's flown to a common location to get the maximum bandwidth. And at that common location, so here you can see like all the hard drives stored there. And at that location, we use a special purpose supercomputer called a correlator to combine the precisely timed data. And once this is done, this is passed onto a calibration stage, which finds weak signals hidden in the correlator output and then tunes parameters to extract a stronger signal. And so actually new calibration procedures had to be developed for this EHT data because it was so messy. The data is so messy compared to other kinds of radio interferometry data, data from radio telescopes, distributed arrays. And so how do we actually, but getting this data was a huge endeavor, but that was just in reducing it to measurements that we could use to make an image. So how do we actually then take this data and make an image? So at this point, we have this data, and we can kind of abstract away the astrophysics of the problem and think about it as purely a mathematical problem. We have this sparse data, and our challenge is to find the image that caused it. And if we were given measurements that covered the entire frequency plane, it would be trivial, because in the case of no noise, you'd simply need to apply an inverse Fourier transform to the measurements to get a picture back. But because we only have a very few number of samples, that means that there's an infinite number of possible images that are perfectly consistent with the data we measure. And on top of that, the fact that there ends up being a very different and quickly changing atmosphere above every telescope across the globe causes our data to be really noisy. And so it makes the problem even more ill-posed than just having the sparse data, much more actually. So I want to give an idea of what this noise looks like, because I like to explain that a little bit because it informs how we actually approach the image reconstruction. So the whole reason that the Event Horizon Telescope works in the first place is due to the fact that light from the black hole is going to travel to Earth for 55 million years, and then as it reaches Earth, it's going to actually reach one of the telescopes slightly before the other one. And that time delay is key for extracting the 2D spatial frequency measurement that's used for image reconstruction. But when you have a telescope in Chile and one in Hawaii and one in Spain, they all have different atmospheres above them. And those different atmospheres cause a different propagation delay in the received signal. And that leads to an additional random phase delay in each frequency measurement. So remember, for every 2 telescopes, we get a complex spatial frequency measurement. Now we're going to randomize that phase because of the atmosphere. And similarly, this atmosphere also causes a different attenuation factor in the signal, causing a changing absolute gain term. And so this error is really challenging because ideally we would have measured this nice, beautiful Fourier component, the italicized D here. But in reality, we have a completely random phase error that happens. And oftentimes, we also have a fairly bad amplitude error. It's not as bad as the phase error, but it's still pretty bad. And so that's pretty terrible, because at first glance, our measurement actually looks nothing like the ideal frequency sample. At first, we've lost both the amplitude and phase. And so if you've lost both amplitude and phase, what really do you have left? But luckily, there's additional structure there. So notice that in this measurement equation, that the corrupting terms are site-based. And every measurement comes from 2 telescopes, right? So the gain error and the phase error occurred at every telescope, but our measurement is from 2 telescopes. So for instance, if we have a 3rd telescope, then the measurements that are formed with that 3rd telescope share some of the same corrupting terms, G2 and phi2. And so we can design imaging algorithms that actually take advantage of this redundant corruption when solving for our images. So essentially, we solve a constrained phase retrieval problem because we can constrain it by the structure in where the errors are appearing in the measurements. And so to do this, we developed 2 kind of classes of imaging algorithms to tackle the problem. The first class of algorithms is based on a very standard method used in radio interferometry for decades called clean with an iterative self-calibration loop. And this is a very traditional method, which is a huge plus because it is very understood and vetted in that community. And so those are kind of like results that they trust. But the big disadvantage is that these methods were not designed for data that is so sparse and so noisy. And so when you're using them on data from the Event Horizon Telescope, you often have to have a lot of guidance from a knowledgeable user in order to get a reasonable result. So because of that, we've been developing a second approach, a class of methods that is more Bayesian inspired, which we refer to as regularized maximum likelihood methods. And in these methods, we don't try to find an inverse function that takes us directly from the measurements to a picture, but instead we try to find a picture that both fits the measurements and what is defined as likely through some sort of image prior or regularizer. And so the disadvantage here is that we have to define what is a likely image. And that's really hard because we've never seen a black hole before. So it's very difficult to decide what should we use as a regularizer that isn't biasing us too much, because any prior we're going to use is always going to bias us, right? But the huge advantage of these methods is that we can naturally incorporate all the different kinds of errors that we expect to see in the telescope data and model that in the data likelihood. So for instance, we can directly try to optimize an image, and we can also just directly optimize an image with constraints that are insensitive to the kind of atmospheric errors that I described earlier. And we typically do that through constraints known as closure quantities. So I'm not going to get into the details of these closure quantities, but I just want to flash them up because I think that they're pretty interesting. So in closure phase, it turns out, remember, every 2 telescopes give us 1 measurement. And so it turns out, and when you multiply measurements, you're going to add their phases. So it turns out that if you multiply the measurements from telescopes in a closed loop, the additional errors due to the atmosphere actually cancel out completely, and you're left with a term that is the same as if you had no atmosphere at all. So instead of just capturing the spatial frequencies, we can capture a multiplication of spatial frequencies and eliminate the error due to the atmosphere and the phase. And similarly, a quantity called closure amplitudes, if we multiply and divide the measurements of 4 telescopes in a certain order, we can obtain a term where the gains cancel out completely, and we're left with a term that is the same as if the gains were all 1 and there was no amplitude error. So I don't want you to have to think about these equations and understand exactly what they're doing, but it's just I think interesting to show you that we can use constraints that are insensitive to these really terrible errors to optimize for the best images. And both of these closure quantities were actually determined a long time ago, but they're typically used for calibration purposes. But rather than just using them for calibration, we actually, because calibration is so difficult in the EHT, we actually constrain these properties during imaging so that we don't assume any calibration whatsoever for them during the imaging process. And so in the regularized maximum likelihood approaches, we do this by solving for an image that best fits these closure measurements, but also looks like what we expect images to look like. So doing this allows us to whittle down from the infinite possibilities to one that we think is a likely image that fits the data well, even in the presence of all this kind of crazy noise. So this is kind of the general, Bayesian approach that we are using, Bayesian-inspired approach, I would say. And so I do want to highlight here for this audience, I'm talking in terms of likelihood and priors, but in reality, we are solving a loss that's just inspired by this Bayesian estimation framework. We have a term that describes the data fit, and one that's a regularizer that penalizes bad-looking images. These are inspired by probabilistic distributions, but we don't necessarily are requiring that in later images that I'm showing. Okay, but note that no matter what method we use to make an image, whether it's the traditional clean method, whether it's a regularized maximum likelihood method, whether we come up with some new fancy machine learning method, no matter what we do, we're always going to have to be cautious. And that's because all methods are going to require that we inject additional information into the problem about what images look like in order to recover something back in the end. And so that's always going to bias our final picture. And we didn't want to, for instance, accidentally inject information that it looks like that our image should look like a ring and then be super excited we got a ring back in the end. So we had to be very careful when imaging to understand what these biases were and make sure that they weren't affecting our scientific conclusions. And that meant a big question we faced in dealing with the M87 data is not just how to make an image, but how do we verify that what we are reconstructing with our imaging algorithms is real? And we tackled this through a multi-step process. So in the first step, in order to avoid shared human bias and to assess common features among, we wanted to assess the features among independent reconstructions. And so to do that, we actually split ourselves into teams. So we had about 40 people who worked on imaging. Either they developed methods or they're just very good at using methods that have been developed already. And we split these people into 4 different teams that globally span the Earth. And when we received the data of M87, we decided, okay, let's go off into our 4 teams and let's not talk to each other about any of the process of imaging at all for 7 weeks. And we tried in isolation to make our best image from the data for 7 weeks. And after 7 weeks, we all gathered together in Cambridge, Massachusetts, and we revealed the images to one another. And this is what we ended up seeing. So this was actually quite amazing. You know, although each picture was different, they all reconstructed the same basic structure. A ring of roughly 40 micro arc seconds that was brighter on the bottom than the top. And seeing these images was actually one of the happiest moments I'd had in the collaboration, because although I had been able to reconstruct an image with my own methods before then, it wasn't until I saw that many different people with different methods and different assumed biases in their methods all kind of recovered the same basic underlying structure that we really built our confidence enough in this result. So doing this kind of blind imaging test definitely gave us a whole other level of confidence in the results we got. But we still wanted to make sure we weren't imposing human bias. So just because we weren't imposing shared human bias, that didn't mean that we weren't all just trying to recover a ring. And so basically we spent the next couple months after getting this initial image trying to break our images. And that led to the second step, where we tried to objective image parameters to remove humans from the loop as much as possible. And to do this, we developed 3 different imaging pipelines that all had their individual knobs on them that are usually tuned by a human user. So you can actually download the code for this is online. You can download our pipelines. The data is online. You can download it, run it, improve these methods. But the thing about all these methods is that they usually have a human that is tuning them. You usually have hyperparameters, and a human is tuning these hyperparameters to get an image out. And we didn't want to have a human tuning them because we might subconsciously want a ring to come out in the end. So instead we said, okay, let's try to search for the best set of settings on these knobs to recover different kind of source structures and see how that is affecting our M87 results. And so, for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk on the sky that had no hole in the center. We made mock data sets from this, and then we tried to tune our hyperparameters of our methods to recover this disk shape. And then when we transferred these exact parameters onto the M87 data, although we had tried our hardest to find parameters that would best recover a disk, we found that our algorithms, when applied to the data, still required us to put a hole in the center. And so by doing this simple training and testing procedure on many different kinds of underlying sources, we saw that our methods always preferred this ring shape. And that was true no matter the day we observed M87 on or the imaging code that we used to reconstruct it. And so by blurring the images from different imaging pipelines to an equivalent resolution, we then averaged them together to form the image that we showed to the rest of the world last year. So this ring of light surrounding a black hole, roughly 40 microarcseconds in size, and brighter on the bottom than the top. So those are the features that we really believe in the image and that was consistent across all different kinds of imaging techniques and parameter choices. But once we had made these images, we still wanted to make sure we still didn't believe them completely. And so we wanted to go through a series of validation tests to make sure that this ring was real. And we did a number of these. I'm only going to talk about one of them today, but we have, but you should go through our papers. We have hundreds of pages of basically validation tests that we did for this. So different kinds of tests.
If I might interrupt, there's a question, why is the gas brighter on the bottom than the top?
Yeah, so it's a really good question. So what happens is we're observing M87 at about a 20, let's say 20 degree angle. So we have the jets that are coming at us at about 20 degrees. And usually people think that perpendicular to that is there's gas flowing around the black hole. So if you've ever seen Interstellar, there's like this ring of gas that's circling the black hole. And so you have that ring of gas that is circling roughly face on to us, but it's a little bit at an angle. It's not perfectly face on. And what happens is when the gas is coming towards us, because it's spinning around so close to the speed of light, as it's moving towards us, it's actually Doppler boosted and becomes brighter. And when it's moving away from us, it's actually dimmer. So we know that if it was a perfectly face-on disk of gas that was spinning around, you wouldn't have an asymmetry. But with it's slightly tilted like that, we know that the gas on the bottom is coming at us, and the gas on the top is moving away from us. Or that's what we think is happening. And so from that, we can tell that the black hole is actually, if you use your right-hand rule, spinning away from us. So that was something that we didn't know ahead of time. But that's what we expect that time variation, that asymmetry to be from. And as I'll show later, we actually see some variations in the brightness because you have this kind of structure of filaments and stuff around the black hole, and that changes over the course of days. But across all days, you still have it's brighter on the bottom than the top, and we think it's due to that Doppler boosting. Did that answer the question?
I guess so. Yeah, that was from chat. So then they didn't say anything, so it seems good. There's another question, if you don't mind, or should I save for later? Or
sure.
It says, why was there as much variance as there actually was among the 4 teams working in isolation? Was this introduced by location differences on Earth, or an artifact of the algorithms they used, or something else?
Why is there so much variation in the images that we got, the first images?
Among those 4 teams, I think they're asking.
Yeah, so I mean, remember, we're working with really sparse, really noisy data. And so there are multiple types of images that, and I'll talk about this more, there are multiple images that are going to fit that data, right? And so if you just stick and you just do if you would place down one prior, impose one prior and solve for the maximum a posteriori image, then it will choose one that is under that prior is good. But different methods might assume different priors or make different assumptions, like of the pixel size or of different things like that, and that will affect the final image you get. Also, clean images are very different than the regularized maximum likelihood images. In clean images, although we have been scripting them more recently, been able to do that. Typically, clean images are done hand done. So you actually are it's an interactive process with somebody who is deciding where the flux kind of should be placed based upon the data. And so that definitely influences also, similar to having a prior influences, a person is influencing it there. But that's why we have the regularized maximum likelihood approaches that don't have the human kind of in the loop there. But I'll talk more about the variations in the images. We expect there to be variations in the images. Okay, so as I talked about, I said that, okay, well, once we had done these surveys with the training data, we could select one set of parameters that perform best on the synthetic data. But really, why should there just be one parameter that we consider? As I just said, there's often many images, many different kinds of images that are going to fit the data. And so by doing large surveys, we see that there's often many parameters that perform reasonably well. And so instead of just picking one set of imaging parameters, we actually decided to find what is the collection of imaging parameters that performs well in synthetic data, and how do those parameters affect the image that we're getting. So for example, for one of the imaging pipelines, the EHT imaging pipeline, we ran hundreds of thousands of different simulations and found that we had about 1,500 parameter settings that we deemed acceptable. For instance, here's a slice of 2 of those in the parameters that we searched over, and the green boxes are showing the parameters that performed well on synthetic data as well. And so by doing this, we could identify reasonable parameter settings that and assess how that affects the M87 data. I also just want to highlight here are a slice of parameters from the Smiley survey and from the clean DiffMap survey. And so once we had these images, about, as I said, about 1,500 different images of M87 from the EHT imaging survey, we could then look across them for variations. So on the left, it's showing the mean image, and in the middle, it's showing the standard deviation. And so this tells us where there are variations in that image. So you'll notice that there are different, like these little knot regions. So those are regions along the ring that we do have less certainty on. But you'll notice the value of the standard deviation of those knots is much smaller than the intensity of the ring. And so if you look at the fractional standard deviation, what it says is we really have a lot of certainty in that ring. It appears in most images. But what we don't have as much confidence is that stuff outside the ring. So all that wispy structure. So you shouldn't believe any of that. So this is a way that we can try to assess variation or uncertainty in our images. But our goal is also to use this image, we want to extract science from it. So we can also characterize uncertainty of image features that lead to science deliverables. So for instance, we could use simple methods to recover the diameter of the ring. And so what we do is we use these simple methods, look over our huge parameter surveys and see how, for instance, the ring diameter changes as a function of these parameters. And doing this, we found that across different methods and across different days, we get very consistent results in what the ring diameter should be, is expected to be. And it converges to something around 40 to 42 microarc seconds is what is found across the different methods and days. And so this is another way that we can get confidence in the ring features that we are recovering. But I do want to really strongly highlight that what we are doing here was probing different modeling choices and seeing how that affected our results. So in the regularized maximum likelihood problem, we were essentially changing something like our prior term and seeing how their prior was affecting our results. And this is definitely something that's important to explore because we do have uncertainty in what our prior should be. But it's also to note that this is not a posterior distribution. And so going forward, it would also be great if we could efficiently explore uncertainty not only due to our prior and data and image assumptions, but also due to the data fit. So in other words, we would love to be able to sample our posterior distribution directly under prior assumptions and see how that affects our results. So how should we do that? Well, one kind of natural approach would be to use something like a Markov chain Monte Carlo method to recover some of these properties or our posterior. And we have done some of this. So for instance, we didn't just estimate ring diameter from the recovered images, but we also did ring fitting. So we fit crescent or ring models directly to the data. So these models were parameterized by a few parameters. And so this is a simulation that is showing optimization of a sampling framework where it is trying to fit a simple crescent model to the data. And when you do this, we get also around 42 microarc seconds for the ring size, which is consistent with imaging. But one nice thing about this is we also get the posterior over the ring parameters. And so in this example, we only had to fit a few parameters to the ring. And so we were able to do that. But it gets very challenging when we want to try to look at posteriors of images because they become very high dimensional. And so to tackle this, we've been developing new methods for efficient posterior exploration. And this is a bit of an aside, but I just wanted to show you some more recent work that's going on in my group at Caltech on this topic and how it's eventually going to feed into future results of the Event Horizon Telescope. So variational methods are a widely used approach to approximating intractable posterior distributions. So instead of directly computing an exact posterior, variational methods assume you have a simple family of density functions, for instance, Q theta here. And the goal is to solve an optimization problem to find the parameters of theta that best match the target distribution, that find parameters theta of Q of theta so that Q of theta best matches that posterior. And so if this ball here represents the space of parameterized models, we might approximate the posterior distribution as indicated by the yellow star with the model parameters theta star. And the traditional way that these models are optimized are by minimizing the KL divergence. So the KL divergence is a measure of how one probability distribution is different from a reference probability distribution. And so here we are saying we want to find the parameters theta of the family of distributions Q that best matches the posterior distribution of our image reconstruction problem. Here I'm just writing out the definition of KL divergence, and you'll notice that it integrates over two terms. The first term is the probability of a sample's image X under your proposed variational distribution, and the second term is a probability of the image given the measurements. And so using Bayes' rule, we can just write out this probability in terms of the data likelihood and prior on the image X. And simply rewriting this as an expectation, we see that minimizing the KL divergence actually comes down to an expectation over the maximum a posteriori loss from earlier with an added additional term that is going to encourage entropy on the variational distribution that we're estimating. And so that's interesting because this first part actually looks like roughly what we were doing with our regularized maximum likelihood methods. But now we're just including this entropy term that basically is going to discourage collapsing to a single solution. And so if we find a theta for this, then we can sample from it to see roughly what samples of the posterior look like for image reconstruction. But then the question becomes, what should our family of variational distributions be? Well, traditionally, they're typically pretty simple, so they can solve these integrals by efficiently evaluating probabilities. But it would be great if we could use a more flexible family of models that's able to better match the posterior distribution. And so this is something that my postdoc Hassan and I have been working on recently. And I believe Huz in the audience, so he's here also to answer any questions if you have any. But what should this flexible family of models be that allows us to well approximate the posterior? Well, as I'm sure many of you are aware, deep neural networks can do this amazing job at modeling complex distributions. So for instance, you can train a neural network to take an image of noise and output a picture that at first glance looks real. And by plugging in different noise images, you'll get actually different output pictures. And so these networks are essentially sampling from a very complex implicit distribution over the space of images. And these deep generative models do a scarily good job at generating samples from high dimensional distributions. For instance, you can log on here to www.which face is real and try to guess which image is fake and which is real. This ends up being the real one here. So for the neural network to do this, it has to be incredibly flexible in order to model all these different correlations and the distribution of real images in order to capture something that is so convincing. And so why don't we use the distribution of this neural network defines to implicitly why don't we use this neural network to implicitly define a distribution as our variational distribution Q and solve for the parameters of the neural network to best approximate the posterior. And so this is an interesting idea, but the challenge of this is that for an arbitrary neural network, just because we can sample from it doesn't mean we actually have a way of evaluating the probability of that sample. And we need to evaluate the probability in order to optimize this equation. But it turns out if the neural network is invertible, then we can actually calculate this probability. So maybe we can use an invertible neural network to define the family of variational distributions we want to search over. And so we do that through a certain class of networks that's gaining more popularity now called flow-based networks or normalizing flows. And these networks are invertible and allow us to estimate the probability of each of our samples X. And we do that, it does this by defining certain kinds of architectures that allow us to invert the samples. And so we use this to define a method for training a variational network to sample from the posterior distribution of images. And we call this deep probabilistic imaging. And so what do we do exactly? Well, we solve for the parameters of a flow-based network under this KL divergence loss. And so to do that, all we have to do is plug in the likelihood and prior constraints exactly like we did for RML. So these are like explicit constraints that we have. And then we train the parameters of a network to produce samples from this posterior, or to approximate samples from the posterior. And so notice that for this, we don't actually have to ask for any training data. It's not like we're training a network using supervised learning and then sampling from it. We're just simply training the network under the loss of the current data and prior constraints to approximate a well-defined posterior. So here you can see an idea on a really simple example of 2D data. So let's say our image was two-dimensional, and these distributions that on the top captured the likelihood of the two-dimensional image under the different measured data. So this is just fake toy data set, but by training our variational approach, we obtain a network that allows us to sample from the distribution shown below. So this is the approximation that is learned for the true distribution on the top. And so you can see, although the estimated distribution is not perfect, it matches a lot of the main features of the true posterior distribution. But let's see what happens in a more realistic case. So on the top here is a synthetic image of a black hole. And we took this image and generated synthetic data from it as if the Event Horizon Telescope were seeing a distribution of this distribution of flux on the sky. And using this mock data set, we ran our regularized maximum likelihood methods to see what we got. And we noticed that every time we ran the method with slightly different initializations, we would recover different results. And so in some of the images, the bright spot was on the top, and in some cases, the bright spot was on the bottom for this data set. And it appeared that both modes fit the data pretty well. So what do you do in that case? Well, we used our variational, this deep probabilistic imaging framework to approximate the posterior distribution. And then when we sampled from this network, we also saw that both of these kind of modes appeared in our samples from the distribution. And so by embedding our images, our samples of images from this network in two-dimensional space, we see that most of our images cluster into two modes with their mean and standard deviation shown to the right for each clustered mode. And the distributions of data fitting loss for each image is shown on the right. And so although it can be difficult to tell which image is correct by inspecting the statistics of a single image, by analyzing the histogram of statistics for each mode, it becomes clear which mode is more likely to correspond with the true image. And so in this case, it turned out mode 2 actually did happen to, on average, fit the data better and did look like the true image. And so this new variational approach gives us a way to efficiently learn and sample from an approximate posterior distribution. And once we have done that, we can visualize the uncertainty. And although I'm not able, because of data policies, I can't show you these new methods on actual M87 data. I do want to just show you what we get when we apply it to on a real data set, a real VLBI data set. So this is an image of the AGN 3C111 that was captured by another interferometer. And in the middle column shows the mean reconstruction that we got. And on the right is showing the standard deviation of samples from the distribution. And since this is real data, there's no ground truth, but we can compare it to an image published using that standard clean technique on the left. Anyway, this was a bit of an aside, but a direction I'm currently excited about pursuing, especially as we start to apply these things to future observations from the Event Horizon Telescope in helping us to understand our image uncertainty. And I'm going to say a little bit more about that in a few slides. But before I go on, I just also want to come back to M87 because I think it's just fun. You know, we've made this really nice image, but a lot of people ask, you know, what did we learn from this picture? And so, for instance, a lot of times I'm asked the question, did we prove Einstein was right? And so the short answer I like to say is, well, no, we didn't prove he was right, but we also didn't prove he was wrong, which is also a big deal too. And so I just want to give you a sense of why that is the case and what we can learn from this image. So for any size object, you can actually calculate its escape velocity. So the critical velocity necessary for an object to launch off to infinity. And notice that this doesn't depend at all on the mass of the object you're launching, just the mass of the object you're launching from. So what happens if the escape velocity is actually more than the speed of light? Well, then light can't escape and you get this dark star or black hole. And so if you took a fixed size mass, you can calculate from this equation how much you would need to compress it down to in order to get a black hole. And this critical radius is called the Schwarzschild radius. But actually what we generally expect to see is not the event horizon itself, but the point at which photons are actually orbiting around the black hole. And that's called the photon orbit. And this is a little bit larger than the event horizon. But actually that's not even what we expect to see, because as photons fly off of this photon orbit towards us on Earth, they get lensed by the extreme gravity, and that ring becomes bigger. So for a non-spinning black hole, the diameter is about 5.2 times the Schwarzschild radius. And if the black hole is spinning, it appears a bit smaller. So this is the range of diameters that we believe a black hole would have if obeying canonical GR. And notice that this is depending on the mass of the black hole. So for a smaller mass black hole, the ring becomes smaller. And that's interesting because actually from past measurements of M87, it was really unclear what the mass was. Gas dynamics pointed us more towards 3.5 billion solar masses, but stellar dynamics pointed us more to about 6.5. So, and stellar dynamics provided this more upper limit. But then we could ask ourselves, how do we turn this into a test of black holes? And so we could look at other unusual and exotic objects. For instance, wormholes also produce shadow features, but for the same size mass, wormholes have a smaller shadow. And naked singularities or super spinning black holes also produce shadows, but they're much smaller even than that. And so it turns out that when you lay the EHT image on top of them all, then you instantly end up ruling out all these other exotic possibilities, and you're left with a ring that matches nearly perfectly with the stellar dynamic measurement of the black hole, obeying canonical GR. So this is kind of just one of the many things we can learn about black holes and gravity by studying this image. But perhaps the most amazing thing we see is that by comparing this picture to simulations scientists have made for years, we find the image taken is actually amazingly consistent with a number of these predictions. But one thing you might have noticed is that this simulation is moving. So you might be curious, is our recovered image of M87 also moving? And it turns out that it actually is. So another interesting thing is that if you we actually observed the M87 over 4 different nights. And if you independently image each of the nights and then string these images together as a movie, you can play them and you can see some evolution. So I'll play it right here. It's really hard to see, so I'm gonna play it again. You kind of see it goes from bright on the left, slightly more to bright more on the right. And so we don't have a very good idea of exactly what is causing this variation. Is it rotation or just material lighting up? And we're actually not even sure where it's appearing in the image for sure, but what we are very sure of is this variability exists. And that's because it appears in the raw measurements we take. And so here you can see the data collected over 2 different nights, and you can see the measurements are statistically very different from each other, which means something has changed. And actually getting a hold on a black hole time variability is quite important for a number of reasons. So it not only gives us a window into the dynamics of the black hole, but an understanding of the powerful jets, but it also helps us in understanding the space-time around a black hole and helping constrain our prediction of general relativity even further. And as awesome as M87 has been, there's actually another black hole the Event Horizon Telescope is interested in that may be able to better answer these questions from time variability. And that's Sagittarius A star, which is at the center of our own Milky Way galaxy. And Sagittarius star is teeny tiny compared to M87, only 4 million solar masses. But because it's so much closer to us, it appears about the same size on the sky. But since it actually is small, that means gas can spin around it much more quickly. And so whereas it takes 4 to 30 days for gas to make a complete orbit around M87, for Sagittarius star, gas can only make a full orbit every 4 to 30 minutes. And so we would really like to take an image of Sagittarius star, and we have been developing ways to do that, but it's very challenging because methods that we're trying to do now, we have to think about recovering not just a static image, but a movie. And so we have this really sparse noisy data. And if we thought solving the problem of recovering an image was ill-posed, recovering the parameters of a movie is even more so. And so as important it is to continue pushing the algorithm approaches to squeeze more out of the data, we've also been thinking about, well, how do we also just improve our instrument to collect data that allows us to do more with it in the future? And so that leads to the last part of the talk today, on using machine learning for optimal telescope design. I know I'm getting, I'm running a little late now, but I think I'll just use 5 minutes to explain what we've been doing here. So in 2017, we observed with eight telescopes, but at 6 different locations. And so making an image was really challenging with that small number of noisy measurements. And although in the end we were confident about our ring shape, it took us over a year to build that confidence. And so we've been building out our array to get more data, adding telescopes in Greenland, France, Arizona, and what I'm most excited about is we recently got funding to add a telescope at Caltech's Owens Valley Radio Observatory in California. And so that's pretty exciting for me. But imagine what could happen if we added 10 more. Well, maybe we could actually make a video of the gas falling into the black hole in the center of our own galaxy. And so being able to do this would be a huge scientific goldmine. But before we just plop down a bunch of telescopes, we have to be really careful. Building a telescope is very expensive, millions, usually tens of millions of dollars. And so we need to be very careful about where we choose where to put them, because we want to get the biggest bang for our buck. And so how should we go about solving for the location of telescopes in the next generation array? Well, typically the design of the sensor is idealized and kind of independently thought of from the image reconstruction problem. So you first just optimize telescope locations, and then you get your data and you try to come up with algorithms to solve all your problems. But when you have so many problems in the data, and the data is so correlated and the noise is so challenging, it's a huge missed opportunity to not consider them jointly. And so because these problems are so intimately related, you should also be trying to optimize them jointly. And so how should we go about doing this? Well, if you rearrange the blocks in this diagram, you'll notice that it looks very similar to something called an autoencoder, where the sensing system, the telescopes, is like the encoder that produces these measurements or codes, and the imaging algorithm is the decoder. And as I'm sure many of you know, deep autoencoders, where the encoder and decoder are neural networks, are often used for image compression, where you're solving for the weights of the neural network that encode the picture in a small number of measurements, at the same time as a network that will allow you to decode that into an image. And so in the image reconstruction problem, you could use an arbitrary mathematical function that takes you from measurements to an image. So you could use a neural network for the decoder. But unlike a generic deep encoder, sensing systems, we have to build them. So they have to obey physical constraints. So we can't just use an arbitrary neural network for the encoder. And so how do we learn something that we can actually build? Well, Hull and I have also been working on this, on optimizing the future telescope placement for the Event Horizon Telescope. And the way we've been doing is we're building a physics-constrained autoencoder. And so how do we do this? Well, from some input image Z here, we can define a forward model of the measurements that we expect to collect, given we have some certain number of telescopes. So in this example, we pretend we had 3 possible telescopes to sample, color-coded red, green, and blue. And we could pass all these samples off to a decoder, to an image reconstruction method, but then that would mean that we'd have to build all of these telescopes. So our goal is to choose among them to find the best to build. And to do that, we introduce this sensor sampling distribution that essentially is characterizing the probability that we sample from a particular telescope. And so we can sample telescopes from this distribution and then mask out any measurements that were not produced by those telescopes. So for instance, maybe just the telescopes 1 and 3 remain. And every time we sample from this distribution, we may sample different combinations of telescopes and obtain different observed measurements. And then once we get these measurements are then passed on to the decoder that allows us to recover an image. So because we can string this together as a single neural network, we can actually optimize the decoder, which is that image reconstruction method, simultaneously with identifying which of those telescopes should we sample. And I'm going to kind of skim over this a little bit, but we use an Ising model to model the sensor sampling distribution, and that allows us to also capture correlations among the telescopes. And doing this, we're able to actually learn the probability distribution of which telescopes are best to sample to get good images from our data. I'll just show this example here. One of my favorite things is being able to, you know, in the case of you having simple Gaussian noise, a lot of times you can analytically try to determine where should you sample. But in the case that you have this complicated noise, like the atmospheric noise I talked about earlier, it's really unclear of where are the best samples. And so, but because we can just train it and we can just plug that as a different forward model in, it's very easy to optimize how telescope distributions would change under these different cases. And so, for instance, here is the result when we assume purely Gaussian noise on the measurements, and you can see it changes drastically when we add atmospheric phase error. So that actually affects what telescopes we should measure. And using this technique, we're determining, you know, which are the best next telescopes we can add to the array, and also how the different telescope selections affect different kinds of features. So maybe instead of doing reconstruction, we want to do feature extraction. And how does that affect the telescopes that are optimal to sample in those cases? And because it's just trained as part of this large neural network, we can just replace the image reconstruction with the feature extraction and still recover what the distribution of telescopes to best recover those properties are. So using this approach, we're starting to understand where we may be placing our next ground-based telescopes to reveal more of the unseen, and also thinking about how we can put telescopes in space and what their optimal orbits could be. And so using this approach, we've learned a lot from the M87 image already, but we're hoping that we can learn even more from future observations. And so what I hope I get across today is that we're really just at the beginning. And now that we have this new extreme laboratory of gravity, we're thinking towards the future of all the different ways that we can improve our algorithms, improve our instrument jointly to learn even more. And so hopefully one day we just don't show you an image, but actually an evolving video of a black hole as gas is moving towards its event horizon. So with that, thank you. I'm happy to take any questions.
Okay, thanks. So I'll clap because I think everybody else is muted, but thanks. I'll allow people to unmute themselves in a second. There's a bank of questions I'll get to. So first one, somebody had a basic question. They said, how do you deal with things that are in the way between us and a black hole, like celestial bodies, gas, dust, stuff like that?
Yeah, so you're looking, well, so there is, when we're looking at Sagittarius star, the black hole in the center of the Milky Way galaxy, there actually is an interstellar medium that scatters our light, the light a little bit. So it's kind of like looking at the black hole through like frosted glass. But because the M87 is out of the plane of the galaxy, it really doesn't affect us at all, this interstellar, well, it's not a noticeable effect, any interstellar medium. Otherwise, we're looking at a very, very small field of view. So remember, this is about 40 microarc seconds in size, which is like, you know, like the size of an atom at arm's length. And so things that are, everything else is kind of, it's going to be basically averaging out over that space. We only are seeing variations on that scale. And also each of our telescopes has, it only sees things in its own primary beam, I guess. So each telescope itself can only see see a focused region. So probably about, I can't remember, 10 arc seconds across. And so, yeah, so basically it's like you're seeing a picture of like you're looking at a picture of a bird on a cloud. You can't see the variations of the cloud because, it's all kind of averaged out when you zoom in on the bird or something like this. So hopefully that answered that question. Actually, so as I talked about at the beginning, M87 has this enormous jet coming off of it, right? And because the Event Horizon Telescope is optimized to see that ring, we don't actually have the short baselines to probe this, the large spatial structure. So actually we can't even see the jet that we know is coming off of the black hole. And so that's one thing that we want to do for when we're adding new telescopes to the array. We want to add more short baselines, which might seem counterintuitive, so that we can actually see the large scale structure that is invisible to us now.
Cool. Okay, so hopefully, yeah, that question, they like that. Another question here is, in one of the earlier slides, it seems like the daily images of the black hole were not too much blurrier than the official image of the black hole. Does additional observation time help increase the resolution at all, or is the resolution limited by the diameter of the Earth?
The resolution is limited by the diameter of the Earth, but I want to make clear that the images that we made in those first images was the same data as the images that were shown later on. Actually, there were slightly different data because it was different calibration that was done for it. It was an engineering release of the data, but it was the same data. It was like we collected data over the course of a week, and then it took us a year basically to reduce that data down to measurements that we could use for imaging. So it's not like we're getting data continuously off of this telescope. We actually have to go to the telescopes, collect the data, and it can only happen like once a year. We actually have to propose for that time to get telescope time. And yeah, so and for different nights, because the Earth is just rotating in exactly the same way, you're just going to capture the same spatial frequency measurement. So you don't get different spatial frequency measurements by sampling different days. You just will improve your SNR, I guess.
Okay, cool. Another, if it's okay, another question in chat is, are there general approaches to try to falsify your best guess prior, or is it mostly tuning to alternate hypotheses and ruling those out?
Sorry, can you say it again? Is there, maybe just state it again, I need.
Yeah, sorry. Yeah, are there general approaches to try to falsify your best guess prior, or is it mostly tuning to alternate hypotheses and ruling those out?
I guess I'm not clear what it means to falsifying the prior. Maybe I think I'm not understanding the question.
No, I'm not sure either.
Sorry?
I'm saying I'm not sure either, but.
Okay, so we try different kinds of regularizers. I didn't really go into them. We have used ones in the past that are kind of data-driven ones, but in the end we decided they were not necessary. We didn't need to have these complicated priors to get a good image, so we wanted to simplify it as much as possible. So we used very standard image regularizers like maximum entropy, total variation, sparsity, things like this that are, go back decades in the literature. And we just used different weights on these regularizers and saw how those weights affected the images. And then we just wanted to find combinations of choices for the regularizers that would perform well on synthetic data. So we weren't, hopefully that answered your question.
Yeah, I hope so. I don't know whose question that was, but I can abuse my power. I had one question. So I thought the center of the Milky Way galaxy was sort of pointing orthogonal to us. Is that incorrect, or?
So I guess you're saying we're kind of in the plane of the galaxy?
That was my understanding, but I don't know.
Yeah. So where for M87 we knew, because we see the jets coming off of it, we know the orientation relative to us. But actually for the Sagittarius star in the middle of the Milky Way, we don't know. We don't see these jets. And so we don't know the orientation of the black hole. So that makes it also really challenging. Yeah, this is a big question. We don't know the orientation. But I mean, let's say you are perfectly in plane. So it doesn't matter what orientation you're viewing the black hole, you're always going to see a ring of light. So because let's say let's say the gas is moving face on like this. Okay, then you see the light because the gas is moving around the black hole here. But let's say it's moving edge on like this. So you have the black hole here and you have the gas moving around it. When the gas is behind the black hole, it actually, because of the gravitational pull, it bends the light into a circle, and so you still get a ring of light around the black hole. So it doesn't matter what angle you're viewing the black hole, you are always expected to get a ring of light. Now, what will change as you are changing your different orientation is the asymmetry. So remember I talked about how when the gas is moving towards you, it's brighter than when it's moving away from you. So when you are more face on, it's going to have less asymmetry. And as you go more edge on, you're going to have more asymmetry because it's moving way faster on one end towards you than the other way. And so when you have an edge on black hole, you might not get a ring per se, but you might get you probably get a crescent, you know. And so that's why you see more of these crescent-y structures. We expected that Sag A star was more edge on, but we really didn't know. We're working on it now.
Cool. Sorry if that was a naive question or anything.
No, definitely it wasn't. Yeah.
Are you okay with one more question, or
Yeah,
you want to get going? Okay, so I saw one more question in chat. So Ken Alexander asked, you mentioned the Ising or Ising model. I don't know how to say it.
Yeah.
Connection with telescopes. Can you elaborate that on a little? Can you elaborate on that a little? What do the two Ising states +1 and -1 at a given site correspond to?
Yeah, sorry, I kind of skimmed through this because I saw I was running late on time.
Yeah.
So basically what we're doing, as I said, we want to solve for the sensor sampling distribution. So which telescopes are best to sample from simultaneously with an image reconstruction method. And so we want to be able we want to determine which telescopes we want to observe from and which ones we don't care about observing from. So we can model it as a binary Markov random field or an Ising model, right? Where because this allows us to say, is the telescope on or off? And so the Ising model parameters are this kind of site activity, which is telling you kind of something like the marginal distribution of wanting to sample from that telescope. And then a correlation between them. So for instance, if I sample telescope 1, am I more or less wanting to sample telescope 5? Because remember, our visibilities our measurements are from pairs of telescopes. The correlation between them is really important. So as just an example here, here is showing the site correlations we get in the case that we assume that we only have Gaussian noise on our data. And as I said before, we have two telescopes and we have two telescopes in Chile and two telescopes right next to each other in Hawaii. So these are going to provide, because the baseline between them is the same, it's going to probe the exact same spatial frequency measurement. So you would ask, like, why would you want to sample the same telescope at different locations? And the reason is because of the noise, because of calibration purposes. But when you don't have that noise, it turns out that, you know, if you're sampling one of those telescopes, it's stupid to sample the other one because it's just giving you the exact same information. So the correlation is telling you the correlation among telescopes and which ones you want to sample together because you want that baseline, and which ones you don't. If you sample one, it's just a waste of your energy to sample the other one. Hopefully that answered the question.
Okay, cool. Yeah, I guess we probably took enough of your time, so I think that's about all the questions we'll ask of you. So I'll allow everyone to get unmuted, and we can say thanks again. So thanks again.
Thank you. Thank you for inviting me.
And yeah, so I guess next time we'll need a large auditorium because this was very big group.
I will use this part as an example. So it's image.
Thank you for your presentation. It's wonderful.
Thank you.
Thank you.
Each task you are given like.
I'm happy to, if someone, I can't, it's hard for me to hear, but if anyone has any questions, I can stay a couple more minutes.
One image for each class, and you will have 5 classes in your task.
I think that was somebody on the phone.
Oh, okay.
Talking in the background.
Is it a question or?
I have a quick question,
Yeah.
if you have a moment. So when you were talking about the site correlations, suggesting that, so is that kind of